Hi there, Honors Chemers. This is Miss Heaton signing in to talk with you about oxidation and reduction. Can you believe that this is our final unit? We are so close to the end of the school year, I can almost taste it. Well, I'm really excited to talk about oxidation and reduction here because this is a really applicable type of reaction. We've actually studied several redox reactions so far this year. Many of these you are familiar with in everyday life, like rusting. That's an example of oxidation and reduction. Fireworks, which produce those beautiful colors, all stem from redox or oxidation-reduction reactions. Bioluminescence of things like jellyfish and other deep sea creatures is caused by redox reactions. This is an MRE, which is used to a lot of times in the military or in, like right after Hurricane Katrina, they gave these to a bunch of people who were living in the Superdome. They use a redox reaction to heat up the food and create a delicious and nutritious meal. And then this here, you may or may not recognize from biology, this is ATP, adenosine triphosphate. You now know that tri means three. There's three phosphates. And this is how we get energy in our cells. And it's a redox reaction that removes the phosphate group. So these are very, very applicable. And we are going to dive right into talking about some of the concepts that are going to be important to practice in class. First of all, we need to know what oxidation and reduction are. And rather than looking at the nucleus, like we were doing in our nuclear unit, we're now looking at the electrons. Oxidation is going to be when something loses electrons. Reduction is when it gains electrons. And these processes always happen simultaneously. You can't just have electrons floating around. They either have to be gained by something or lost by another. So we call this redox for short. It's a combination of reduction and oxidation. Let me give you an example of how this works. Solid sodium can combine with chlorine gas to make sodium chloride. And we know that this is an ionic compound. Sodium by itself has no charge, chlorine has no charge, but when it gets into a compound, sodium is +1 and chlorine is -1. Folks, we've gotten kind of lazy about whether we're putting pluses or minuses or including the charges or including when we're not supposed to. In this unit, it's going to be super important that you pay attention to when the charges are there and when they are not. When they're in a compound, they have those charges, and here's why. The two sodiums have combined with a chlorine molecule, and we know that sodium has one valence electron, and chlorine, 1, 2, 3, 4, 5, 6, 7 each. And when they're in this compound, they each have 7. And what happens is sodium will donate one of its electrons to chlorine, making it Cl-. So then it will have 8 electrons around it, and sodium will have no valence electrons. And the other sodium will do the same thing. It'll give its 1 valence electron to this chlorine that had 7. So now each of them independently will have 8, which is why they get the -1 charge. So in this case, sodium has lost an electron. So sodium is oxidized, and chlorine has gained an electron. So it is reduced. And it might seem kind of strange that it's being reduced if it's gaining, but it has to do with it goes back to the days when they didn't know about electrons, and oxidation was what happened when something would then combine with oxygen. But here's what you need to remember. I have a couple memory devices for helping you remember which is which. You can take your pick. I like oil rig because it's a nice, beautiful picture. This is like the BP oil spill. We've got oxidation is the loss of electrons, while reduction is the gain of electrons. Or you could think about Wizard of Oz. Leo the lion says, grr. If something loses electrons, it's oxidation. The gain of electrons is reduction. So take your pick which one you want to use. Now, it's not always as easy as I showed in that example with sodium and chlorine. Sometimes we have to assign oxidation numbers to keep track of the electrons in each atom of a compound. This may or may not be the same as a typical charge. You can't always assume that if it's in column 1, it'll be +1. There are some rules, and hopefully you have this handout. If not, you may want to go online and download it or copy it down. We're going to go through these rules and explain them step by step so you can apply this in class tomorrow. So if an atom is an ion, so that's represented by having a charge, that oxidation number for the atom is going to be the same as its charge. So this hydrogen has a plus, so it has an oxidation number or oxidation state of +1, whereas the oxygen would be a -2 oxidation state. Now rule number 2 says that if an atom has no charge, if it's just an element by itself, it has no oxidation number. So here we've got 2 hydrogens. each hydrogen would be 0. Here we've got oxygen. Each oxygen would be 0. And here we have a magnesium. This magnesium would be 0. These are all zeros, and those are O's. Now notice that we're assigning an oxidation number to each atom in an element or a compound. Rule number 3, oxygen is usually -2. There is an exception, we'll come back to that in a minute. This will be common because oxygen is often oxidized or reduced. So in this compound, oxygen is -2. And rule number 4 kind of goes along with our example here. For hydrogen, the oxidation number is generally +1. And so here we've got an H, and an O. And each oxygen will be -2. Each hydrogen will be +1. Notice that this kind of leads up to our 5th rule. Oh, nope, not our 5th rule, our 6th rule. We'll come back to that one. Rule number 5 says that there are some groups on the periodic table that commonly have certain charges. So if you remember our periodic table here, we've got 6 rows over here, a D block in the middle, and then 2 over here. This first row, the alkali metals, is +1 for oxidation numbers in compounds. Group 2, the alkaline earth metals, is +2. The boron group with aluminum in it is generally +3. Again, this is only when they're in compounds. And halogens, which are not the column with helium, but it starts with fluorine, those are generally -1. So in this compound, we'll go back to our previous 2 rules. Oxygen is -2, hydrogen is +1, and sodium, since it's in this column right here, is +1. Now, notice in our examples for Rule 4 and Rule 5, if you add up all the oxidation numbers, what do they add up to? Well, 1 + 1 - 2, that adds up to 0. 1 - 2 + 1, that adds up to 0. And so that's where our 6th rule comes in. In a neutral compound, meaning a compound with no exponent at the end, the sum of all the oxidation numbers of all atoms present must add up to 0. And so let's look at our example for rule number 6 here. We know that each oxygen is -2. So we'll put that up here. So we know that each oxygen is -2. And there's 4 of them. So altogether, those oxygens are going to contribute -8. We know that barium is in column 2. So its oxidation number is +2. And so we can figure out what sulfur would have to be in order to make it add up to 0. So what number would we need to put here? 2 + what -8 gives you 0? Well, that would have to be 6. So sulfur's oxidation state would be +6. Notice that sulfur is below oxygen, so you can't assume that it's just going to be -2. It depends on the compound that it's in. And there are some elements that often change oxidation numbers. Now that we've talked about Rule 6, let's go back and talk about Rules 3 and 4 and their exceptions. There are a few compounds where you'll see oxygen not be -2. And that's a peroxide, where you have 2 oxygens in a compound. So here you have 2 hydrogens and 2 oxygens. We know that it has to add up to 0, and hydrogen is +1. And so if each oxygen was -2, it wouldn't add up to 0 overall. So each oxygen here will be -1. So in a peroxide, each oxygen has an oxidation number of -1. That's not very common, though. Don't worry too much about that. Hydrides are another exception. We said hydrogen is generally +1, but Rule 5 is more important. Sodium will always be +1 in a compound. So in order for those oxidation numbers to add up to 0, hydrogen has to be -1. So the exception is that in a hydride, where hydrogen is at the end of the compound, it has a -1 oxidation number. And these numbers kind of tell us whether whether the atom has more electrons, if it's negative, or less electrons, positive, than it used to, similar to what a charge tells us. And last but not least, for a polyatomic ion, the oxidation numbers have to add up to the charge, and that's the exponent at the end here. I'm going to switch colors of ink because it's getting crowded here. So we know that each oxygen is -2. And we don't know what carbon is, but we could figure that out by adding up all the oxidation numbers to see what they add up to. Since the charge on carbonate is -2, and we've got a carbon that we don't know, and then we've got 3 oxygens that are each -2. So what -2 - 2 - 2 gives you -2? Well, let's combine these. That makes -6. So carbon would have to be 4, because 4 - 6 gives us -2. So carbon would be +4 here. And you can apply this same thing to a compound. I'm going to move this over here so we can see a little bit better what's going on. NH4 2 SO4. So this has 2 polyatomic ions in it. We can break it up into NH4, which we know has a +1 charge, ammonium ion. And there's 2 of them, so we're going to write those separately. And then we've got an SO4, which we know, because we memorized it, has a -2 charge. So let's figure out the oxidation number of each element, or each atom in these compounds. So let's start with our sulfate. We know that each oxygen has a oxidation number of -2. So let's figure out what sulfur would be. 4 oxygens, each with -2. Sulfur plus that has to add up to -2. So sulfur minus 8 is -2. So sulfur would have to be +6. So oxygen is -2, sulfur is +6. Looking at our ammoniums, both ammoniums are going to have the same, each hydrogen is going to have the same. We know that hydrogen is generally +1, and there's 4 of them. So nitrogen, which doesn't have a rule on our list, we can figure out by comparison. There's 4 hydrogens, each that are +1. We add up the oxidation numbers, they have to add up to +1. So nitrogen would have to be -3. So each nitrogen is -3, each hydrogen is +1. Notice that we are assigning an oxidation number for each atom, not the multiple of how many oxygens there are. So oxygen is not -8, it's -2. Okay, let's try just a couple more examples. I like 4, 5, and 8, and I'll show you the answers here at the end in just a minute. So if you want to pause and work them all out, feel free, that'd be great practice. What we're going to do is identify the oxidation number of the underlying atom, because that's the unique one. So here, sulfur, we don't know. Oh, we know that oxygen is -2, and there's 3 of them. So 3 times -2, those have to add up to 0 because there's no exponent. So sulfur minus 6 equals 0, so sulfur would have to be +6. Hey, I think it was +6 up here. Does it always have to be +6? Actually, you'll see in the next one that it does not have to be. Sulfur here we don't know, but we know oxygen is -2. And there are 4 oxygens. Uh-oh, maybe this does turn out to be 6. I might be wrong. Yeah, sulfur minus 8 is -2, so sulfur is still +6. Uh-oh. You'll have to take my word for it for now that sulfur does not always have to be +6. We'll see that in a later example. Okay, and one more. Potassium, K. Oh, we know that K is +1 because it's in column 1. It's in the alkali metal group. There's 2 potassiums, and there's 2 chromiums, and there's 7 oxygens. Oh, you know what? This is a great one to break into a polyatomic ion. See the dichromate ion? So in this we have a dichromate, Cr2O7, and we know it has a -2 charge, and you've either memorized that or you can tell because it's with 2 potassium ions. So within this, let's see, we know that it has to add up to -2, and each oxygen we know is -2. That's a hard and fast rule. So we've got 2 chromiums. This is a really important example to pay attention to, folks. And there's 7 oxygens, each with a -2 oxidation number. So 2 chromiums minus 14 adds up to -2. So we'll add 14 to both sides, and so 2 chromiums have a total oxidation state of 12, which means each chromium is +6. Notice that we assigned it to each chromium, not the 2 chromiums together. Okay, let's pause. I'm going to show you the answers to the others, so if you would like to pause for a minute and give them a shot, feel free. Okay, here are the oxidation numbers for the underlying compounds in the examples before. If you have any questions, please shoot your teacher an email or make sure you ask that question in class tomorrow about how those were obtained.